welcome to all the attendees, and we are happy to have Professor Jornet, who kindly accepted the invitation to be with us here in our CSIM seminar series. Today he will be talking about unleashing the spectrum above the 100 giga, from theory to practice. Professor Jornet is widely known. He is associate professor at the Department of Electrical and Computer Engineering at Northeastern University. He received the BS and MS from UPC Barcelona and the PhD from Georgia Tech. He is, as I said, widely known with many awards, many participations. He is ComSoc Distinguished Lecturer, and he is editor-in-chief of the Elsevier Nano Communication Network Journal. Well, with no more introduction, we thank you again for accepting the invitation to be here. If you can please, yes, I see that it's done. So yeah, the floor is yours, and yeah, I will be muting, so feel free. Okay, for the people attending, if you have questions, you can write them on the chat, or you can wait until the end of the talk so that you can ask in person. Thank you again, and please, the floor is yours.
Perfect. Thank you very much, and again, thank you for the invitation. As some of you know, this is a topic that I'm quite invested into, and I'm always happy to share what's going on and what are the latest results. So today I'm going to be talking about unleashing the spectrum above 100 gigahertz, and it's not just theory. As you will see, it's a lot of experimental results too. So let's do this. Look, as you know, the discussions on 6G have started, and there are still, not agreement of what's going to be, right? And there are academics, there is industry, there is everyone, but there is one number that keeps coming on the table, and this is that the peak data rate in 6G systems is expected to reach 1 terabit per second. Now, how can we get to 1 terabit per second? Well, the question is, how much bandwidth do we need to do this? And it all comes down to what type of modulation are we going to be using, so the modulation order that we'll utilize, and how many parallel channels we can utilize if, for example, we're talking about a MIMO system. This is what we show in this figure, which is, once again, how much bandwidth do I need to get to 1 terabit per second as a function of the number of MIMO channels and the modulation order. What happens here is that, well, unless you really have very high modulation orders, like a 1034 QAM, and a very high number of orthogonal channels, let's say 64, you're going to need a very large bandwidth. Like only when you have high number of channels, high modulation order, you may be able to deal with, let's say, 2 gigahertz. And just for everyone to remember, right, in 5G and R, our bandwidth is 400 megahertz, or at most 800 megahertz when you aggregate those of 2 channels in millimeter wave. So we're talking about that, but also, we're close to be able to have this very high modulation order with this very high number of parallel channels. The reality is that more than being on this end of the table, we'll probably have to be on that other end of the table. So we're going to be dealing with very large bandwidth. Now the question is, okay, where do I find these bandwidths? Well, let's just think. This is a frequency axis from 0 to 10 terahertz or more. Every single wireless communication system that we are utilizing today, or I would say 99% of them, are under 100 gigahertz. That's where we find everything that has to do with wireless, not just communication, but I'm also talking about radar, GPS, different type of atmospheric sensors, weather forecasting sensors, everything, it's there. Of course, the result of that is that there is not much bandwidth for everyone. So if we want to enable 1 terabit per second with this very large bandwidth, we need to go somewhere else. Someone may say, if bandwidth is the only driver, why don't we go to optical frequencies? And absolutely, there is no problem with looking into optical frequencies. And today we're not going to talk about those. The question here is, why would we skip this spectrum between, let's say, 100 gigahertz and all the way up to 10 terahertz? Why would we give up on this spectrum? Well, the answer is that we don't want to give up. This is the spectrum that is known as the sub-terahertz and terahertz band, or sub-millimeter waves, depending on the community that you're talking to. And this is what we believe it's going to play a key role in 6G. And by we, it's okay. When we start working on this over 10 years ago, there were not many people. The reality, as you know, is that in the last couple or 3 years, there have been many academics and companies jumping into this. And it means that finally these things are going to happen. Now, what can happen at terahertz frequencies? Well, we start talking about communications, right? And we said we want to get to terabit per second links where? Well, in personal area networks, or in local area networks. The reality is that when we start working on terahertz, we thought that given the channel conditions that we will study later today, and given the technology, which is we don't have that much transmission power, these terahertz communications were only good for short distances. And that's why for many years we used to present terahertz communications in the context of short range. But the reality is that we have really improved the technologies, improve the signal processing, and improve the understanding of the channel in such a way that today we can talk about, for example, terahertz wireless links for backhaul applications, or we're not afraid to say that we can use terahertz communications in the context of inter-satellite links or even space networks. The key idea here is the following. When terahertz, imagine that your next 6G phone, among many radios, it comes with terahertz. Terahertz is not just going to be for a few elites, right? Terahertz communications have also the opportunity to bridge the digital divide and again, utilize terahertz connectivity for things as the ones we mentioned, backhaul, on the ground, or even in the sky or in space. Now, this is only half of the story. What is the other half? The other half is sensing, wireless sensing. Now, sensing means different things to different people. When we talk about terahertz sensing, we can mean many things. We might be talking about radar, and you know that the higher the frequency, the smaller your wavelength, therefore the smaller things you can see. At the same time, the larger the bandwidth, the more accurate that you can see the things. Fine, so you can do much better localization if you go to terahertz frequencies. Fine. At the same time, terahertz radiation, it's non-ionizing, so terahertz radiation cannot break molecules, but terahertz radiation interacts with the molecules and atoms of several materials. In fact, this is a property that far from being a problem, it's an opportunity, because through these interactions, we can create what's known as non-damaging imaging or spectroscopy, which means that we can not only know where there is something, but also what is this something made of. So we can identify a target, where it's positioned, the shape of the target, but also the material that it's built of. And this is an opportunity that cannot be done at lower frequencies because the photons of lower frequency signals do not have enough energy. But we can do that at terahertz. And well, as you may know, at the same moment, there are already satellites with terahertz radios orbiting the Earth. But those satellites are not doing communications. They are not using the terahertz radio for the communication. They are using the terahertz radio to understand both atmospheric signals, so radar of the composition of the atmosphere, but also to listen to signals that come from deep space, because it was shown several years ago that a very large percentage of the energy emitted since the Big Bang is in fact at terahertz and infrared frequencies. So for example, it's NASA or the ESA in Europe, the major investors in the development of terahertz sensing technology. So for example, we can leverage this terahertz technology to study climate change. And the fun thing is that you don't need to do this separately. This can be the same technology. You can be using it for communications and sensing at the same time. And again, this is a topic that many people are talking about, joint communications and sensing for this, for that. Usually, they mean for radar. What we're saying is that at terahertz frequencies, you can do much more when it comes to sensing than just joint communications and radar. But for example, joint communications and atmospheric studies. Now, let me give you a couple of snapshots of how these things may look like. Joint terahertz communications and sensing in indoors. Well, we could think as, of course, we are indoors. We can utilize highly directional terahertz links to close the link. Terahertz signals, as we will see, cannot go through obstacles. So once again, we might have to rely on intelligent reflecting surfaces, something that you will, again, it's another hot topic, and that's great. At lower frequencies, if you allow me, and I always like to say messages to piss off some people or just to trigger some people. At low frequencies, intelligent reflecting surfaces are an interesting add-on, but networks at lower frequencies work even without intelligent reflecting surfaces. When you get to terahertz frequencies, the blockage problem is very real. Therefore, there might be many cases that if you don't have an intelligent reflecting surface, you may not be able to close your link. So we'll talk about this a little bit later. The key idea here is that all these transmitters, receivers, surfaces are not just enabling communication. We can, if we properly design the signals that we're sending, and we do our signal processing right, we can utilize the same set of signals to, for example, understand the occupancy of the room if we're trying to have a controlled environment, and at the same time monitor the quality of the air that these people are breathing. Again, this monitoring of air quality, it's something that terahertz signals can do because they interact with the air we breathe. Sometimes you can think of this as a problem. Oh, there is absorption, and we'll talk about absorption. But at the same time, you see it as a possibility because it means that there is a way for signals to interact with the environment much more than what they do at lower frequencies. We show you an example indoors. Let's go to the other extreme, which would be, let's go to space. As of today, as I said, there are many satellites orbiting the Earth. These satellites are mostly performing radar, atmospheric radar, or a spectroscopy, characterizing the atmosphere or listening to the signals that come from space. But we can also use these satellites, of course, for communications. Right now, for example, if you think of a Starlink and SpaceX, it's mostly millimeter wave for the up and down links. And as of today, it's mostly millimeter wave between the satellites. The reality is that they are trying to push to optical frequencies. One thing that we're saying is like, look, if you are above the atmosphere, your channel at terahertz frequencies looks very nice. So there is no reason why you may not want to consider terahertz communications for that too. And at the same time, you do this, and with the same signals, you are collecting those other sensing information. So that's an interesting opportunity. Now, so far we have talked about the applications that relate to things that we're used to see, right, in the macro scale. But there is another set of applications very interesting, which relates to the use of terahertz communications for very, very, very short range. We call them nanoscale communication networks. And the idea with nanoscale communication networks is that when you go up in frequency, your wavelength becomes smaller. So you can do radios, including the antennas, the different waveguides, the different building blocks of your radio can be done in a very small scale. Therefore, we can use these terahertz radios, for example, to create wireless networks on chips. And there are several projects, including those like at UPC in Barcelona, looking at how to create a new generation of computers in which you have not just a few cores, but many, many, many cores in the same integrated circuit and all exchanging information wirelessly. But we can also use these applications for things like wireless nanosensor networks or the Internet of Nanothings, which is all something that we envisioned when I was still a student with Professor Ian Achilles at Georgia Tech, which, you know, it's eventually happening, right? This was in 2010. Now we are in 2022. And one thing that once upon a time it showed crazy, now it's actually closer to reality. And the same with this wireless nanobio communication network. So terahertz communication can also transform healthcare. This is an example of such an application. So joint nanobio communication and sensing. The key idea here is that if you go to Google right now and you look for nanosensor or nanobiosensor, you will easily find around 100,000 publications of people mostly working on developing structures, this plasmonic nanobio chip here, which react to terahertz and optical signals in different ways, depending on the type of biomolecular components that they have been exposed to. So these are things that people have been building, but right now what they do is they take a sample from your body, they put it on this sensor, they put it under a microscope and look. We believe that we can transform this by actually implanting this type of devices few millimeters under the skin and then externally exciting these devices utilizing wearable devices that, again, in 2010, this was like very far-fetched, but today everyone has some of them. And of course, eventually cloud connectivity. So all these are applications which are interesting. And it made me think, okay, so if all this is happening, why don't I have already a terahertz radio on me, right? I have so many wireless devices. Why don't I have something with terahertz frequencies in it? Well, the reality is that there are many challenges. Challenges that go all the way from the fundamental physics of the materials with which we build the radio to the physics of signal propagation. What happens to these electromagnetic waves as they propagate? And only when we understand both the materials and the devices and the propagation, it's when we can start designing the signals. It's then that we will talk about communications and signal processing. It's then when we can try to build not just one link, but a network. So we need networking protocols. And of course, for anyone to be able to adapt this technology, we need to be able to legally use it, so policy and regulation, and we need to standardize it. So more elements, more agents can enter the market and compete and eventually get a better service or a better product to the user. What we're going to do in the rest of this talk is go block by block, some more details in ones than the others, but try to provide you a sneak peek about where is Terahertz today? Not where was it 10 years ago. Where is Terahertz today? How far we are, and what are the things that still need to happen? So hopefully some of you get excited and decide to join us. So let's just start talking about materials and devices. Look, for many years, every paper on terahertz communications would start, there is this terahertz technology gap, which means that there are no terahertz radios. And this was true in 2009 when we started working on this, and that's why some of our papers starting like that. But we're in 2022. Many years have passed, and many things have happened. So let me tell you where we are in terms of terahertz technology. And well, let me tell you up front, you cannot go to Amazon to buy a terahertz radio, but you can get terahertz radio somewhere. Let me share that with you. First of all, what do we mean by terahertz technology? Well, by terahertz technology, we have mostly three things. Let's start with the first. We can call something a terahertz radio if we're able to do what? If we're able to generate, modulate, amplify, filter signals which are at carrier frequencies in the terahertz band, so 100 gigahertz, 300 gigahertz or more. So signals in the hundreds of gigahertz or more with multi-gigahertz bandwidth, right? Remember, the motivation to go to these terahertz frequencies is not just that we want to go high in frequency so we write more papers. We want to go high in frequency so we get the larger bandwidths. Therefore, as important as at which frequency you work is how much bandwidth do you have. Now, what has been happening? Do we have these devices? Do we have these analog front ends, devices that generate the sinusoidals, modulate them, amplify them, and filter? Well, the reality is that there has been a lot of progress, mostly following three paths: the electronics, the photonics, and the plasmonic path. The key idea here is that we could spend an entire, as I said before, this is part of a 10-hour course or a whole semester long course if you want. The key idea is what I can tell you now. It's like electronic devices that can be used for terahertz radios as of today are the ones that can give you the highest power. And for example, here in this figure, we show you a couple of transceivers, in particular, the one that you see here in the front. It's a terahertz radio operating between 200 and 240 gigahertz, which offers 200 milliwatts of power. 200 milliwatts of power, it's a lot for terahertz standards, again. And this is a device that comes from NASA JPL. So this is a device that was developed in the context of sensing that then we repurpose for communications. Fine, that's the electronics path, and usually has to do with up-converting frequencies. So you start from a microwave signal, and you send it through a series of non-linear devices which act as frequency multipliers. Imagine you have your sinusoidal at a given frequency, and you send it to a device that computes the square of the signal, or the power of 3 of that signal. What does it mean? That you generate a lot of harmonics, some of them at the double frequency or at the triple frequency, depending on your multiplication order. And then what do? You select and amplify the harmonic, and that's how you keep going up in frequency. Fine. The other approach is the photonics approach. And in the photonic approach, the idea is that you start from very high frequencies, optical frequencies, and then you multiply lasers, for example. And the result of multiplying two lasers is that you get the double frequency, like always, but you also get the difference frequency. And that difference frequency, if you engineer the wavelength of your lasers, can be a terahertz signal. The other option is the plasmonic path, and I'll show you a little bit more about that. That's a little bit more of a futuristic option, but I'll justify later why we have that. Still, this is the way you get 2 terahertz signals, but then you need to radiate them. And that's the second key component of a terahertz radio. What do you mean? Well, I need to be able to control the radiation of terahertz signals at the transmitter, at the receiver, but also in reflection, if we talk about intelligent reflecting surfaces. As we will see, if we don't have much power and we need to go through the channel, we're going to need high gain directional antennas. Just think in the following way. The higher the frequency, the smaller the wavelength. Therefore, your antenna, which is proportional to your wavelength, becomes very small. So even if it's a very efficient antenna, the amount of radiation that it can intercept, it's very small, which means that, well, then you don't want to send the power all over the place. You want to focus your power to that tiny antenna that you have at the receiver. That's why we need high directional gain. Of course, in addition to antennas, we can look a little bit at optics, which again, terahertz is between microwave and optics. So we can look a little bit at optics and leverage things like lenses, programmable lenses, or even metasurfaces. And again, the key idea is that even if you need high gain directional antennas, at terahertz frequencies, these are going to be very small. For example, what you see here on the left, it's a tiny horn antenna, which is less than 1 centimeter and gives you around 25 dBi of gain in such a very small structure. Now, people usually stop here, but there is a very important third box that we need to build our terahertz radio, which is that we need to be able to process these signals digitally. My computers are digital. How do I interface my digital computer with actually an analog radio? Well, I need data converters. And what's the challenge? Well, remember, you will say, oh, but these data converters operate in baseband. Of course they do. But the problem is that we're trying to operate with signals whose bandwidth is 10, 20, 50 gigahertz. So you need such huge bandwidth that you need very, very fast data converters, whether it's digital to analog or analog to digital. And the reality is that there are some solutions which are extremely expensive, power hungry and everything, or you may have to, maybe we need to start thinking how do we get rid of, for example, the Nyquist sampling theory, right? That it comes to that. Some of the things we're doing now, for example, is to leverage highly parallelized systems in which maybe we don't have a single data converter that is very fast, but we line up many of them and then we do frequency multiplexing to be able to create signals whose aggregated bandwidth is as much as I would like to use in the terahertz band. Fine. These are the devices. I've stopped. Well, I still have 2 slides on the devices, but we're almost done. Let's talk about the channel. Now, okay, we have devices, not too much power. What happens to these signals as they propagate? Well, as you may know, at terahertz frequencies, we do have a huge bandwidth, but this comes at the cost of a very high path loss. Or does it? Let's look. People, when usually think of the terahertz channel, the first thing they tell you is like, at terahertz frequencies, you have this absorption, so, you know, the channel is horrible. Well, let me show you this figure. This is loss as a function of frequency, and only between 100 gigahertz and 1.5 terahertz. So a zoom in the lower part of the terahertz band. Now, do we have absorption? Well, let's look. The solid lines in this figure, the ones that are blue, red, or yellow, the solid lines are the absorption lines. And yes, there are frequencies in which your absorption, it's easily more than 100 dB or more than 150 dB, which is very scary. But the reality is that between these peaks, between these spikes, you have frequencies in which the absorption is very low. And you will say, oh, but Josep, you were telling us that there is so much bandwidth that suddenly we need to peak. Well, just think between these 2 spikes, like between the one before 600 and the one before 700, there are almost 200 gigahertz of bandwidth. In other words, we can move all the spectrum that we're utilizing today under 95 gigahertz fits within one window in the terahertz band, and we have many of them. So is there absorption? Yes, there is. But is this absorption affecting me? It depends. If you properly pick your waveform and you properly pick your carrier frequency, you should not be worried about absorption. Now, does it mean that the terahertz channel is great? No. As I was telling you already, terahertz antennas are very small. So if you let your signal go everywhere, if you just emit with an omnidirectional dipole, you're going to have very high free space losses. Well, the solution is that we don't want to be sending the signal everywhere. We want to focus the signal, so we need directional gain. And of course, if we're building a network, that directional gain needs to be dynamic, right? We need to point to the users how to move this and that. The third problem, which is perhaps a little bit more of a problem, it's blockage. And indeed, terahertz signals, they can go through some materials, but they don't really go through anything that is too deep. And by deep, I mean, they don't go through people, they don't go through dolls, they don't go only through some glasses and plastics. So that's a problem, right? So we have blockage. And how do we overcome blockage? Well, through reflecting surfaces, whether they are smart or dumb. A piece of metal is a good reflector. So if you strategically position somewhere, that can help. But I think we can do better today, as we will see later on. Now, whether it's for this directional gain that needs to be dynamic or reflecting surfaces, one thing that I didn't mention before and that now I want to talk about is, well, we talk about building a radio, but to do all this beamforming or control reflections, I need arrays. How far are we with antenna arrays? Well, when it comes to antenna arrays, experimentally, what has been shown today, and actually for several years, are radios that operate mostly under 300 gigahertz. So you may think that that's the high millimeter wave, the upper millimeter wave, and that's true, right? I mean, there is always this discussion, is this millimeter wave or is this terahertz? Let's just call it sub-terahertz if you want, and that's fine. There have been these arrays for several years now, like for example, Professor Kaushik Sengupta, when he was a student, he was already working on terahertz arrays. Now he's a professor, associate professor at Princeton, so he's doing this type of things, great. The group out of the University of Santa Barbara, or the Communications and Sensing and Terahertz Frequencies, they have also been developing arrays, again, between 100, 200, maybe a little bit more gigahertz. We're talking about mostly electronic arrays, though people are also working on photonic arrays, which can offer you 8 parallel digital streams, okay? But then what happens is that for every element, every stream may have to go itself through a directional antenna, because if not, we're dealing with very weak signals. The main problem to make arrays with more elements, which on paper it's very easy to write, but in reality it's very difficult to achieve, is that the antennas become very small, but everything else, the way to generate a signal, these frequency multipliers, these mixers, these amplifiers, they become small, but not that small. So the challenge is, how do you pack in the same chip, a chip that can be as small as this, how do you pack in this, not only the antennas, but all the active circuits? So packaging becomes a challenge. Now, at this moment is when I want to bring back that we said, look, there are mostly 3 approaches. We talk about the electronic, which is to take a frequency, a low frequency, and push it up. And we talk about the photonic, which is to take a high frequency or wavelength and push it down. And all these systems are frequency converting systems, which means that, well, they are complex. And as you know, every time you generate a conversion of frequency, you're generating harmonics, not only the one you want, but also other harmonics that you don't want. So by definition, this is not energy efficient. So could we do something else? And the answer is yes, that's actually what we have been working on, which is, can we leverage new materials, and not just your silicon or 3-5 semiconductors, but can we leverage materials such as graphene to build devices that intrinsically operate at terahertz frequencies? And that's what we have been looking at. And for example, it has been quite some time now that we have been working in utilizing graphene, which is a 2-dimensional material. This material was obtained for the first time in 2004. We started working on this in 2009. You will see some of the earlier references on the antennas. And there was a huge boom, especially in Europe, about how good is this graphene material. The reality is that graphene turned out to be not good for many digital applications, but it's great for applications that require high speed in the analog domain. And that's exactly what you need to build a front end, right? You need analog components that can generate, modulate, ideally amplify, and then radiate signals. So we came up across a way in which we can generate terahertz signals on chip with a device that the device itself is less than 1 micrometer in one dimension and maybe 2, 3, 4 micrometers in the other dimension. So we're talking about being able to generate on chip a terahertz signal directly, just connecting a battery and utilizing less than 10 square micrometers of footprint. We actually built some of those. We are talking about utilizing the same material to be able to add information to this on-chip signal. So to be able to, for example, implement a QPSK, if that's what we want. And we are also talking about being able to radiate these signals utilizing graphene. Again, so graphene is the connecting block for the generation, the modulation, the radiation. And as you can imagine, there are not just us, but other groups working on this and exploring if, for example, we can use this type of structures for amplification or filtering. The goal here of what we did with Professor Akildis was, once again, it's not just a matter of writing papers, it's also seeing the value that technologically this may mean. So also we actually obtain patents for all these things. Now, these elements are very small. I'm talking that in total, look, your antenna is 1 micrometer. Your modulator is going to be 1 or 2 wavelengths at most. Your source, it's even less than a wavelength. So this is very small. This is not going to give you a lot of power. We're talking about powers of a few microbats. But what I'm telling is that your entire radio, it's again around 10 by 10 square micrometers. So what can you do with such a small radio? Well, you can start making arrays, and not just array of antennas, but arrays of every element, every RF chain on the antenna. That's the key idea. One of the things is that by using graphene, you can make things very small. Actually, you can make things smaller than the wavelength, because your antennas, your wavelength, when you deal with graphene, it's not your regular wavelength, but it's what we call the plasmonic wavelength, which is smaller than your free space wavelength. So you can make very small elements And we studied the mutual coupling between them, and we showed that we can also put them very close together. And this was exciting. And with this, what can we do? Well, this is why actually, 5 years ago, or more, 6 years ago, we introduced the concept of ultramassive MIMO. This is the first paper that introduces this term. Now people are reusing this term for different things. Just to be clear that when we conceive ultramassive MIMO, it was not just to make massive MIMO with more antennas. It's actually to leverage the properties that new physics and new technologies give you to be able to do, again, not just things like the beamforming or the spatial multiplexing, but for example, being able to do spectral ultramassive MIMO. So have the same radios sometimes operate at different frequencies, even within the same array. And of course, we want to utilize this in transmission, in reception, and reflection. In the previous paper, we showed a vision and how we can get to that. In this other paper that we published a couple of years ago with my student Arjun, we actually showed a specific realization of a plasmonic architecture that can get you there. Now, these are still transmission and reception, but as we said, we will need probably intelligent reflecting surfaces. Is this something new? Absolutely not. Intelligent reflecting surfaces have existed for decades, right? They just became popular recently. Some people claim that they discovered intelligent reflecting surfaces. Well, maybe they should have done their literature search, but even at terahertz frequencies, right? So there have been reflecting surfaces, programmable reflecting surfaces at terahertz frequencies for 10 years or more. The key idea, however, is that to make these surfaces controllable, you need something that is tunable, and that it's tunable at high speed. At lower frequencies, the intelligent reflecting surfaces, you normally utilize a diode that you can switch on and off, or you utilize a controllable capacitor that allows you to tune the reflection coefficient of each and every one of the elements. At terahertz frequencies, we don't have diodes that turn that fast. We don't have any capacitor that can work at these frequencies. But surprise, we have been talking about graphene being a good material, that it's tunable and that operates at terahertz frequencies. So that's interesting. The only thing is that graphene, it's not a good reflector. So there have been some papers saying, oh, let's use graphene to make reflectors. I'm telling you, a piece of metal is a much better reflector than graphene, but graphene is tunable. So what we did, again, with Arjun a couple of years ago was to show that why don't we combine the two walls and we use metals like gold, right, as the reflecting element, but then we utilize graphene to build a stub, which means to make a controllable element that we attach to the antennas. At the end of the day, what happens is that you make this in a photolithographic process. So it's not that you go antenna by antenna, you just make it all at once. But we utilize graphene to control the reflection coefficient of every element. Then it's when you have your intelligent reflecting surface. And what we were able to show is that in terms of a strength, again, if you had a metallic controllable element, your reflection can be very strong. If you use only graphene, that's the red line, your reflection is actually going to be very weak. When you create a hybrid structure, you get tunable as opposed to just metal, which is not tunable, and you get much more power than if you only use graphene. And we showed all these in different types of scenarios, including not just the typical study that many papers show, which is what happens when the wave is orthogonally hitting you. Now, what happens when your signal comes at an angle? We show that we can actually reflect in different types of angles. Fine. Now, one thing, and this is just to show you what we think should be happening next. Look, if we're investing a lot of money in making these transmit arrays, receive arrays, these reflect arrays, and we only use them to just direct the signal one way or the other, we are missing, and we're missing a lot. Let me tell you why, because the key idea is that with these structures, we can not just send the signal in a direction, but we can also change how the signal looks as it comes to us. In other words, we can engineer the wave front of the signal. Let me explain this a little bit better. So usually, again, people in optics are much more used to talk about wave fronts. At lower frequencies, we usually deal with Gaussian beams, which means beams that after the near field, you just have a diverging beam. And that's why you have an antenna array or a directional antenna that will control that opening of the beam. And that's fine. But the reality is that we can do other type of beams. We can change how the signal behaves as it moves, not just the direction, but how it looks like. And for example, we can talk about bezel beams. Why would I do bezel beams? Well, bezel beams are specific type of beams that have these rings. They are hollow in the middle, depending on the order. Bezel beams, for example, are what is known as self-healing, which means that unless all the rings are blocked, even if just some of the rings can go through an obstacle, then this beam will regenerate itself. This is a very known property of physics. People in optics have leveraged it before. For the first time, we can have a technology that can leverage this for example, terahertz frequencies. So it makes sense to look at that. But there are other types of beams. For example, we can talk about 80 beams. 80 beams are beams that they are designed to propagate and then turn without anything. There is nothing here. Your antenna is here on the left, your array. You send the beam, and then your beam will bend towards the side that you designed them. And to make these different type of beams, the only thing that you need to do is to control the amplitude and the phase at every element at your transmitter. Well, we can do that, right? Of course, not only that, we can control how the beam looks like, but then we can also add information to it. And usually when we think of information, we think of waveforms, so how the signal changes in amplitude, phase, or frequency as it propagates. We can also talk about polarization, but for example, we can also talk about orbital angular momentum, which means that if you look at the wave propagating, you can make the signal twist over itself. And depending on the angle at which you twisted your signal, you can actually generate different modes. And the beautiful thing, and again, this is very well known in optics, this is not new physics. This is something that at optical frequencies has been done many times, at lower frequencies sometimes, but now we have a technology that can allow us to make this practical. The key idea of OAM is that different OAM modes are orthogonal. So you can think of this as a way to implement MIMO even if your channel is scarce, because you are going to have orthogonal channels generated directly at the transmitter. So again, some thoughts coming out about that, which is great. Now, we talked already about this technology, the propagation, and now we were talking about wavefronts, and we mentioned waveforms. Well, question, what should be the waveform for 6G terahertz systems? Well, first of all, to design a terahertz communication system, we need to do many things, right? So first of all, we go to terahertz frequency so we can talk very fast. So as you can imagine, time synchronization is going to be challenging. We are dealing with clocks at very high frequencies, many times generating through frequency up and down conversion processes. So frequency and phase synchronization become challenging too, because we do have phase noise. The other thing that we need to do to send information is that we need to be able to estimate the channel and equalize it. And when you deal with a channel which is 30 gigahertz wide or more, well, channel estimation becomes a little bit challenging. And once you have those done, then you need to think, okay, and what type of modulation do I use? Well, let me talk about a little bit more about modulations for 6G terahertz. And let me tell you, I don't think we know yet what's going to be the waveform for 6G, or at least for 6G terahertz. Is it going to be OFDM? Is it going to be a single carrier OFDM, like DFT spread OFDM? Or just we go back to regular modulations? Well, we don't know just yet. We know that there are many options, and I'll show you later. We have pretty much tested everything that you can think of. We're still not convinced. Let me talk about some of the different modulations, not just your typical OFDM with more subcarriers or your typical, QPSK. What are other modulations we can use for terahertz frequencies? Well, if you're thinking of short distance in which you're not going to find many molecules of water, therefore there are not going to be those spikes. If you think of short distances, we can think, for example, of utilizing pulses and build systems like an impulse radio ultra-wideband that instead of operating between 3 and 10 gigahertz with sub-nanosecond pulses, we're operating between, let's say, 0.5 and 2 or 3 or 4 terahertz with sub-picosecond pulses, or pulses which are in fact 100 femtosecond long. These pulses, which are shown here in the right, very short in the time domain, which means very broad in frequency, right? The shorter in time, the fatter in frequency. These pulses are not something just to write theoretical papers about. These pulses are commonly used in terahertz time domain spectroscopy platforms. Remember, I said before having communications, people have been using a terahertz sensing for a while, including material scientists that are trying to understand the properties of different materials. In many of these applications, they use these very short pulses, and these pulses, we can very simply build a communication scheme. If you have a pulse, you have a 1. If you don't have a pulse, you have a 0. We work on these pulses for several years. We had a few papers. We showed that indeed these pulses can allow for very high data rates, can allow for multiplexing of many users in space, because you really need to be unlucky if you want your tiny pulses to overlap with other users' tiny pulses. But these are all great for short distances, but the moment that your distance increases, let's say 1 meter or more, absorption will enter the game. So a lot of your power, which we don't have more from the start, right? We don't have much from the start. Tons of your power will be absorbed. So maybe we don't want to use that. In fact, when we go to higher frequencies, we may want to pick one sub-window in the terahertz band and do something good within it. Even when we look into one sub-window, what's going to happen is the following. Let's look at this. This is, for example, the channel response. So, in fact, 1 over the absorption losses as a function of frequency for the frequencies around 1 terahertz. What I'm showing here is, again, if we didn't have absorption, this line will be a straight line at 1. But because we have absorption, and there is an absorption line around 980 gigahertz, and there is an absorption line at 1.09 terahertz, what happens is that you see this shape. This is the result of absorption before and after your window. What happens is that when you increase your communication distance from 1 meters to 10 meters, of course, you're having more absorption, so your amplitude reduces. And you will say, Josep, everyone knows that the farther you go, the weaker your signal becomes. What's new? Okay, this is not what's new. Now let's take these lines and normalize them. Let's take the blue line, normalize it by its maximum. Let's take the red line, normalize it by its maximum, the same with the yellow, the same with the purple. Look what has happened. If we're able to compensate for power, that's fine. But when I go from 1 meter to 10 meters, what's happening is that my bandwidth is shrinking, and not because of me, because of the physics of the channel. So molecular absorption, as you increase in distance, it's not that it becomes just stronger, it becomes broader. So there is this broadening effect that will make your useful frequencies smaller. And because of that, we'll need to have modulations that can at least deal with this system, ideally exploit this system. And for example, we have been working for a couple of years now on hierarchical bandwidth modulations, or modulations that the key idea is that maybe some of you are familiar with the concept of hierarchical modulations or concatenated modulations. The idea is that you send one stream that is the result of concatenating, for example, 2 QPSK modulators. The first QPSK, the second QPSK will effectively create a 16 QAM. Now, if you have a good channel and if you are a good receiver, you can recover the 16 QAM. If you don't see a good channel, at the very least, hopefully, you can recover the original QPSK. Fine. This has been done already. And for example, it's used in satellite communication systems. But what we're saying here is that it's not a matter of just concatenating modulators. It's also a matter of operating the different modulators at different symbol rates. In other words, if you are close, you can refresh one of the modulators faster than if you are far, because if you're far, your bandwidth is smaller. So we showed the different trade-offs. Should you allocate more power to the near user or to the far user? How do you pick the bandwidth? How do you do the information coding? Do you want to send the same stream with more resolution, or do you want to send totally different streams to the near and the far users? We had some work on this. We have a journal now under review. Hopefully we hear about it soon. And as many of these things that I'm showing you here, we actually experimentally tested them. We'll show you later what did we use for that. The other thing that I many times get, it's like, Josep, this is great, but I cannot really think of an application in which I need 1 terabit per second. And I agree, right? That right now we can think of extended reality, great. Maybe in backhaul applications, yes, we'll need to aggregate all the millimeter wave flows from every user, so we'll need that. But in many cases, we might not need this very large bandwidth. So what can we do instead? Well, maybe it's time to reconsider the concept of a spread spectrum, but now not to spread spectrum over 100 megahertz of bandwidth. How about spread spectrum over 100 gigahertz of bandwidth? What can we do with that? Well, we can increase the security of our systems, because if we're using secret orthogonal spreading sequences, we're going to be great. We can facilitate coexistence, and that's another hot topic, because what's really happening these days is that we're going to higher frequencies. The sensing community, including those who are doing Earth and space exploration, they are also using those frequencies. and they are very, very, very sensitive. So we need to be careful to not interfere. Well, one option is that why don't we adopt spread spectrum, and we do that to reduce the power density at any given frequency so we don't interfere with others, whether they are from the same system, whether they are active users like radar but narrowband, or whether they are passive sensing users. The reality is that we have actually designed an ultra-broadband spread spectrum system. We presented this in DISPAN at the end of the last year. And again, this is yet another option. Don't make me decide just yet which should be the one for 6G. What I'm just telling you is that there are new opportunities for things that at some point we move from. The other thing is that there is another type of modulation, which is a spread spectrum, which is chirp spread spectrum, which is interesting itself. And this chirp spread spectrum, the key idea is that some of you may be familiar. This is very similar to what's used in LoRa, but it's also utilized a lot in radar, by the way. The key idea is that these are waveforms that are very robust to frequency selectivity. So it was Priyanshu, one of my students, who said, look, if we use a frequency selective robust waveform, can we also communicate over the absorption lines? And that's what we showed a couple of years ago, which is like, if you utilize chirp spread spectrum, you're able to communicate over you're able to communicate over the terahertz band, even when partially crossing some of the absorption lines. Fine, so there are opportunities. That's the message that I want to tell you here. Now, what do we do with networking? Because we have been talking about one transmitter and one receiver. How do I make a network out of this? Well, if you remember, when we teach networking, usually when you get to the link layer, for example, what you say is that, well, at the link layer, you have medium access control because you need to make sure that the users do not utilize, we need to make sure that the most scarce resource, which is the channel bandwidth, is fairly used by everyone. The reality is that at terahertz frequencies, there is bandwidth for everyone. So, we don't really need to fight for the channel. But what becomes challenging is to get synchronized. Because if everyone is using these very high directional antennas, that's going to be a problem. And again, how do we even know when everyone is, right? And how then I build multi-hop links? So we have some early solutions, but I do think that much more is needed. And for example, we have been thinking of, if you think of your typical medium access control protocol, starting from Aloha, going to the most purely redefined CSIM CA version, usually we have the transmitter leading the effort. What we're saying here is that, well, maybe we want to shift this and have the receiver lead the effort. In other words, if you want to talk to someone, you know that you want to talk to someone, but that other someone doesn't know that you want to talk to him or her, right? So maybe we need to go from the typical transmit initiated scheme to a receiver initiated or to a polling scheme. You can have a receiver that is very quickly scanning space. So through beam steering, very quickly scanning the space. And for every slot, for every direction, for every sector in which we reach, it asks, is there anything for me? Yes or no? You will say, oh, but polling may not be that efficient, this and that. Well, we actually end up showing that the beauty of going at terahertz frequencies is that you can communicate very fast, right? So you can effectively be exploring the space, so turning your antenna and sending short messages very quickly. Again, you're doing this at terabits per second link in such a way that you don't need to spend too much time in any specific sector. Even if there is data for you, you can communicate it so fast that at the end of the day, honestly, what's going to be your limit is the propagation delay. And in fact, we showed that. So we had another paper building on top of this idea of receiver-initiated scheme. This was with Danny, in this case was a visiting student in our lab. We have actually several visiting students. It's always great to get new ideas from collaborators. So what we end up showing here is that, we can do some fine-tuning of the protocol, and we can really, through this type of protocol, show you much better throughput, which is what people seem to forget. It's not, we don't go to the terahertz band just so when you get lucky, you get 1 terabit per second, right? We go to the terahertz band so we can offer you good service. So we showed actual service approaching or exceeding even 100 gigabits per second at the link layer, actual throughput. That's interesting. For these works, we utilize a simulation platform that I will explain in a couple of slides. The other thing that we have been looking at is at neighbor discovery. And again, at millimeter wave frequencies, we already had to go through many of these things. At many points, however, at lower frequencies, what we assume is that at least one of the nodes can operate in quasi-omnidirectional mode. But the reality is that, well, at terahertz frequencies, we need everyone to be very directional or we are not going to close the link. So what we said here is like, look, instead of trying to look for the maximum where you and I are, let's assume that everyone in the network, when we enter into neighbor discovery mode, starts turning around. What we showed is that even if you and I never get aligned, if I have information about your entire radiation diagram, including the side lobes, I can understand where you are just by looking at, say, 4 or 5 consecutive samples of your signal as you are turning. This is a very short explanation of what we did in this paper, but this is actually a work in which we show that we can much quickly discover where everyone is by leveraging the full antenna radiation property. This is true for any directional system. Of course, if you're at terahertz frequencies, everything is faster because you can complete any transaction much quicker. But for example, for this, we showed this and we experimentally validated with a millimeter wave testbed because we don't have antenna arrays at terahertz frequencies in my group, but it worked. The other thing, again, you are trying to build multi-hop links. We know that relaying is good, right? We studied it in many frequencies. The key idea is the following. Usually, you say, look, if instead of talking directly the transmitter with the receiver, I have some relay nodes in the middle, I can reduce my power, so everything is beautiful. Fine. The key idea here is that if you put relays between a transmitter and a receiver, first, you don't need that high gain directional antenna. So you can operate with broader beams, which will expedite all your neighbor discovery, all your medium access control. At the same time, if you're talking to users who are closer, then you have more bandwidth. So it's not that you can just save power. You also have more bandwidth. So you can also be faster at the physical layer. So you can be faster at the physical layer, faster at the link layer. Of course, there is going to be latency issues. You're going to deal with the memory of every node. So there are challenges. So what we did here, it's not to tell you a definite answer, but to build a mathematical framework in which we explore all these cross-layer effects. And sure, even when you know that you have to relay every 10 meters, how do you find them? How do you find the best route, knowing that your nodes are turning around, trying to talk to different people? So we had some very early ideas that are still growing on how we can route. And the idea here is that, look, everything happens so quick that maybe it's okay if you don't send your information through the best route. Maybe you just want to send it to anyone who is available. This type of hot potato routing is something that has been done before in for example, wireless network on chip at optical frequencies. And it's something that we think it has also future when it comes to mobile ad hoc networks at terahertz frequencies. Now, I mentioned 2 things. I mentioned that some of these networking results, we use a simulation platform. In particular, this is TeraSIM. TeraSIM is an NS3 extension that we developed in our group and that now other groups are supporting and maintaining. It incorporates already the models for the channel, for the antennas, and even a physical layer. So if you don't like that much, all that physics part that I've been talking about or the signal processing, you can start building your higher networking protocols onto this, explore traffic models, explore different routing strategies, explore anything you want to utilizing this. And again, this is available officially in the NS3 App Store. And yes, we maintain it. And again, other groups are contributing to it. Now, one thing that we said, and very quickly because I know I'm over time. So we said, if we want to use any of these things, we need to be able to legally use the technology, right? So regulation becomes very important. And again, it was not until 2019 that in the US, the FCC made it easier for people to be able to access licenses to operate radios at this frequency. The problem is that you can ask for experimental licenses, but there is still the problem of many frequencies not being available contiguously because of the passive users. So this is something that we're still working on. And yes, we need standards. And there is a standard for terahertz communications. It's from IEEE 802.15 group, was approved in 2017. It's only for point-to-point links, but it's a good starting point. And what I would say is that if you're interested in standardization, which again, our work should not just end up in papers, right? Should not just end up being, an idea. If we want our work to have an impact, we need to fight for this work to be part of a standard and eventually part of a line of products that everyone will use. So these groups, you can join. The discussions these days are mostly virtual and remote. So I would invite you to join these type of things. Talking about, again, the regulation, that's what I said. I mean, this is a snapshot of the spectrum above 100 gigahertz up to 300 gigahertz. We think that there is a lot of bandwidth, and the reality is that there is absorption line, but there are also these gray bands that we cannot utilize. So what we're working now here at Northeastern in collaboration with different institutions is try to push the FCC and the ITU for them to let us share the bands that are gray, which are right now are forbidden bands. One more thing, I talk about the testbeds that we have. This is the Terranova platform. It was the first, and still today it's the largest and only platform that can simultaneously communicate what I would say is at legacy 60 gigahertz, but more importantly, from 120 to 140 gigahertz, from 200 to 240 gigahertz, and above 1 terahertz from 1 to 1.05. At 1 terahertz, there is an absorption line, so we need to be a little bit after that. We can operate at these frequencies with very large bandwidth of right now up to 32 gigahertz of bandwidth per channel. But this is a platform that keeps growing. So we have many transmitters, many receivers at these different frequencies. We have different ways to operate the signals. Sometimes if you need to test like channel or physical layer, we can utilize offline signal processing techniques. So we utilize MATLAB to design the signals that then with arbitrary waveform generators, we inject to the testbed, or through an oscilloscope, we digitize, and again in MATLAB, we process. But sometimes for applications like the networking, like medium access control or relaying, what you need is a system that can react in real time. So in that case, we're developing that radio frequency system on chip base or FPGA type of platform. So again, the testbed has many parts, the analog part, the digital part, they are all exchangeable, different type of antennas. And with this, we have done many of the experiments that we showed. So things above 1 terahertz. We have actually demonstrated multi-kilometer, multi-gigabits per second links around the 300 gigahertz window. We have demonstrated the spread spectrum and other things that hopefully we can share soon. I'm not saying this just so you say, oh, you see this, lucky guy can use this. No, I'm saying this because this is part of an NSF grant for which we are expected to, let anyone use this platform. So what I'm telling you is, you have any new idea of new types of waveforms, maybe any new idea regarding, I don't know, some machine learning based channel equalization or an autoencoder you pick that you would like to try at terahertz frequencies, reach out, we can work with you. And actually, we even have some data sets already published, everything available in the lab website. Last but not least, let me just tell you, many of these tests that we are doing, we can do them at Northeastern because we are part of an FCC innovation zone, or in other words, we can communicate at pretty much any frequency that we want to without much hassle. Right now, we mostly can operate, we can do this type of terahertz experiments in 2 areas. One is the rural area, one is the urban area in Boston itself. That's where we are. That's what you see in the background. But we also have a satellite campus, which is outside of Boston, which is more of a suburban or rural area in which we can also do that type of testing. So we can do testing in urban, suburban, and rural areas. We are not the first FCC innovation zone in the country, but right now we are the only one that allows or supports the wireless communication at frequencies above 100 gigahertz. And again, with this, what I'm trying to say is that if you think of any experiment that you would like to try, and maybe you don't have the hardware, or maybe you have the hardware, but you don't have a license, we are happy to work with you to make this happen. With this, I think I talked too much, but I guess we are done. Conclusions, you can have them on your own. I think that I tried my best to highlight what's done and what's not done at the different layers. And with that, just thank, of course, this is not, by no means, this is a one-man show. This is a large group of students from all over the world at different levels, from first-year undergraduate student to PhDs and postdocs who work together. With this, I stop talking, and I'm happy to see if we have questions. Thank you.
Thank you, Giuseppe, for a very interesting talk covering so many topics, and I'm really impressed with the testbed. Okay, and I'm really happy to know that it is open, so that anyone can really deploy some tests there. So, questions from audience?
I know it's a lot of information, so probably people need some time to digest, which everyone can follow up by email.
Yeah.
I try to get back to people.
It's okay. It's okay. Yeah, I have actually a couple of questions. The first one it's a very easy, straightforward one. So I heard you just now saying multi-kilometers coverage.
Yeah.
So you really reach the multi-kilometers with the terahertz band?
Actually, yes. let's see how much I can say about this. So this is a paper that is supposed to come out soon in a journal that cannot be mentioned. So having said that, this is a very interesting project. Actually, this corresponds to the picture down here. This was a link around 225 gigahertz in which we utilized the up and down converters from our collaborators at NASA. So remember I mentioned some of the best terahertz technology comes from the people who are doing sensing. So the same group who developed the radios for these satellites that are orbiting the Earth, we collaborate with them. It's Jose Siles and Imran Mehdi and a few others at JPL in Pasadena, California. What we did is combine with them some of their devices, which were designed for sensing, so they are not the nicest when it comes to large bandwidth. But then what we do is a little bit of a custom signal processing block at the transmitter and the receiver, so we can, instead of suffering from the non-linearities of the hardware, we take advantage of them. So we were able to show a 2.03 kilometers long link transmitting 4 gigabits per second of data. So there was data in it, and utilizing antennas which were only 40 dBi. Why do I emphasize this? Because there have been some papers of multi-kilometer links around 200, 300 gigahertz, but they come with these very big dishes of 55 dBi at the transmitter and the receiver. We were able to do that with 40 dBi, mostly because two things. The technology of the NASA guys, it's very good. And for example, it was last year that we signed a Space Act agreement with NASA JPL for the exchange of, again, not just technology, but also students. So right now, one of my students, well, Ali, he spent already some time with them, and now he's going again this summer. That's a healthy collaboration. But also, in addition to the technology, is let's tailor the signal processing. Many times we wait for device people to do what we want, so then we can just go with our traditional schemes. What we did here is tell us why you cannot give us much power. Oh, that's the problem. Then maybe I can tailor my signal processing around. So I cannot say more than what I already said, but as soon as that paper is out, I'll share it.
Okay, perfect. Okay, good. So I have a question here from the audience. Amr Al-Wakil is asking, yeah, thanks for the interesting talk. In terms of localization, what is the location accuracy that can be achieved by terahertz?
Very good question. So on the one hand, there is the limit of the wavelength. And again, if you are at 300 gigahertz at the very beginning, it's going to be 1 millimeter. If not, could be more. The reality is that the bandwidth plays a key role because you might be able to see things, but you will not see them clearly. For example, right now with 20 gigahertz of bandwidth, around, let's say 100 or 200 gigahertz, with 20 gigahertz of bandwidth, we can go down to 1 centimeter. That's something that we feel comfortable now. But if you go through the limits of the physics and not the limits of what we done, it's millimeter scale. So we can do 1 centimeter today. We should be able to get down to millimeters. That's what we're talking about. If you instead of 300 gigahertz, you go through 3 terahertz, then you can get sub-millimetric. And some material scientists, colleagues, or let's say more device colleagues who are looking not even at 1 or 2 or 3, but are looking at 4, 5, 6 terahertz, they are really looking at material imperfections at the micrometric scale. But for radar, localization, long-range sensing, not just super near field sensing, sub-centimeter mix. I'm very comfortable to say that. We are doing that today. Millimeter will be doable. Yeah.
Okay, thank you. So another question, yeah, it is a thanking message. I have another question. So whenever you commented about the spread spectrum. So the spread spectrum will also cover the bands with the molecular absorption and they can overcome them, or it is only when in these windows that are away from the absorption loss?
Very good question. So the way we design, so when we talk about spread spectrum, we talk about mostly two. The direct sequence spread spectrum, what we have tested so far is between absorption lines. However, to go over the absorption lines, we went to the chirp. Could we use, and again, this is another form of spread spectrum. Could we use the direct sequence spread spectrum or CDMA within absorption lines? We could. We just know that chirp is more robust against frequency selectivity. Will the other work? Well, it could. Right now, the way in which we have done it so far is CDMA type for within the lines, chirp spread spectrum when you cannot control if you need to go over the lines.
Okay. Well, I have so many questions. I'm so interested in the topic, but yeah, let me. I know the people they want to leave. Okay, it's a 1 hour talk, so
we can always
one just last question. The effect of the absorption. Why it got broader? I really didn't get it. Whenever
that's
you.
a very good. That's another very good question. Let me go back to that slide. Yeah, and believe it or not, I mean, I should not say this type of things, especially when I'm recorded, but there are some papers out there in some good venues with some wrong figures, which is, it's the following. So what happens is the following. So why do I say that there are some papers with wrong figures? Look, let's look at the lines, at the solid lines with the spikes, right? Let's pick, for example, the blue line. You will find some papers in which you see that there is the blue line and then the exact same blue line, just 20 dB up or 40 dB up. And they say, look, as you go to different distance, there is more absorption. And that's wrong, because what happens is the following. And this was studied in this very first, I mean, the model for this was in this very first paper in which we presented a very accurate physical channel model. Then we have used that model in different ways. One of them is to show this broadening. The idea is the following. At the end of the day, this absorption, let's assume that you only had one water vapor molecule, which is the main absorber at terahertz frequency. Imagine you only had one molecule. What happens is that the photon energy of your particle has enough energy to make the molecule vibrate. And this vibration, this is a mechanical process, right? So your photon energy needs to be precisely the energy that this atom needs to start shaking. Fine. If you have now more molecules, well, if you are at 0 Kelvin, meaning if you're totally cold, what will happen is that you would have a perfect straight line with absorption, even if you have many molecules. What happens is that if we are not at 0 Kelvin, that we are at room temperature, and you have many molecules, these molecules also interact between them. And what happens is that the more molecules you find, the more interactions that there are. So you don't just see the absorption exactly at the frequency, at the wavelength or frequency that you expect, but also around it. And the more molecules you find, the more, not random, because it's really around one frequency, but the more dispersive this absorption is. So that's why when you increase the distance, you find more molecules. So the more molecules you find, the broader the absorption is. This is something that, again, the type of theory to model this, it's called, I mean, this is mostly theory developed in the context of sensing. And this is theory that for people who are doing sensing, this has been known for a while. However, they didn't really look at it from communication perspective. That's our job. That's our job. That's the theory, sorry, the name that I was looking for, it's radiative transfer theory. And there are even books on that. There are even books on that.
Okay. Thank you very much. One last comment from the audience, well, from the remaining people in the audience. So they say, why you look into direct spectrum to DSSS and not into the multi-carrier CDMA?
Well, I mean, as I said, we don't know which one should we be using now. We started with what we thought it makes sense. Would we use multi-carrier CDMA? Sure, yes. And if you want, we can try it. That's the reality. We started with something that was easily to tell people, which is like, direct sequence of spectrum. It shows very simple. It's easy to implement because at the end of the day, I only need one IQ stream at the end of the day, and I can do it easily. But can we try other solutions? Sorry, here's where I'm trying to go. Can we try our solutions? Yes. You pick.
Yes, it is an open area for innovation and research.
Yes, exactly.
Okay, so well, with no further questions, I think that we come to the end, and we thank you again for the interesting talk. We will share it with our colleagues in our website and YouTube channel. And it has been really a pleasure to hear to everything that you have done on Terahertz. Very impressive. So thank you again, Professor Jornet, for accepting our invitation and for being here. And thank you all for joining, and see you in next CSIM seminars. Thank you all.
Thank you.
Thank you. See you. Bye-bye.